Welcome back to the deep dive. Okay, today we're getting into something really fundamental to how things move in industry.
That's right. We're talking about the muscle behind the machines.
Exactly, pneumatic and hydraulic system controls. The things that make giant excavators dig or robotic arms assemble things with, like, incredible precision.
Even things you might not think about, like a dentist's chair moving smoothly.
Right. So our mission today is, well, to cut through the jargon a bit. We want to really unpack the core ideas, the key parts, and just help you get a solid grip on how these powerful systems work.
We'll be using some standard technical curriculum as our guide, but making it make sense.
Yeah, showing how simple liquids and gases get harnessed to do some pretty amazing work. Because honestly, these systems are everywhere. Understanding them is like a shortcut to understanding a huge chunk of modern technology.
It really is. And what's fascinating here is how these systems, which can seem complex on the surface, actually rely on some very basic, fundamental physical principles. That's what makes them so versatile and so powerful.
And using fluids to transmit power, that's the core concept, isn't it? A key skill for anyone involved in, say, industrial automation.
Absolutely. Or even if you're just curious about how the industrial world, works, it's all about moving energy from one spot to another using a fluid.
Okay, so let's kick things off right there. The basics. When we say fluid here, what exactly are we talking about? Is it just water or oil?
Good question. So in general physics, a fluid is anything that flows, right? But for these power systems, we're focused on two main types.
Which are?
Gases, usually compressed air, and liquids, typically special hydraulic fluids.
And there's a key difference.
A massive one. And it defines almost everything. Gases can be compressed. Think squeezing a balloon. Liquids, for all practical purposes, are incompressible. Try squeezing a bottle full of water, it doesn't give.
Okay. Compressible gas, incompressible liquid. That's the heart of it.
That's the core distinction. Beyond that, they both, take the shape of their container and flow along the path of least resistance.
Got it. So that incompressibility or compressibility, how does using these fluids for power stack up against, like, old school gears and levers or just using electric motors directly?
Well, if we connect this to the bigger picture, fluid power has some really distinct advantages. First, you get huge force and torque from relatively small components, much smaller than an equivalent electric motor sometimes.
Right, look at a digger arm,
Yeah.
tiny cylinders, massive force.
Exactly. Second, they're great for both straight line, linear motion, pushing, pulling, and rotational motion. Some mechanical systems are better at one than the other.
Okay.
Third, control is often simpler and very precise. You use valves to easily manage the direction, the speed, the force, even the torque.
And safety must be a factor too.
A big one. You generally reduce risks like electric shock or sparks, which is crucial in, say, explosive atmospheres, and less fire hazard compared to some electrical wiring or even hydraulic oil sometimes, though oil has its own considerations.
So where do we see these typically?
Oh, everywhere. Car hoists in garages, that's hydraulic. Airplane landing gear, hydraulic. Those throttling valves in process plants, often pneumatic. Automated assembly lines, usually a mix of both.
Okay, that really sets the scene. Let's dive into one of those. Air power, pneumatics. Why is compressed air just so common in factories, with robots, on assembly lines? It seems almost too simple.
Well, its simplicity is a huge part of its strength. The fluid is just air, which, once you compress it, is super cost-effective and obviously available everywhere.
So compressed air is the medium. What are the big wins for using it?
Several key advantages. Storage and transport are easy. You fill up tanks with compressed air, pipe it around a factory, gives you loads of flexibility.
Right.
Plus, building automated sequences is pretty straightforward with basic valves and actuators. Easy remote control.
And you mentioned safety earlier.
Definitely. Air isn't flammable, no sparks, great for hazardous spots, and no hydraulic oil spills to worry about causing fires or contamination. They're often quite robust systems, too, often needing less maintenance than, say, complex electrical setups.
Cleanliness must matter too.
Absolutely. If you filter and dry the air properly, it's a very clean power source, essential for food, pharma, electronics, industries like that, and a neat little efficiency thing. You often don't need return pipes. The used air just vents out.
Faster than hydraulics sometimes too, you mentioned.
Yeah, they can achieve higher cycle speeds in many applications, which is a big plus for things like high-speed packaging or assembly.
Okay, sounds almost perfect. But I'm guessing there's a catch. The flip side.
There always is, isn't there? It's important to be balanced. Generally, pneumatics deliver lower power output than a hydraulic system of the same size.
Okay, less muscle.
Right. And while air is free, the whole system, compressor, dryers, pipes, can sometimes end up being more costly initially than maybe an electrical or hydraulic equivalent for certain jobs.
Mm.
And this is a big one: contamination. Dirt, dust, water vapor in the air. They are the enemy. You have to get rid of them with filters and dryers, or your efficiency plummets and components wear out fast.
That makes total sense.
Yeah.
So keeping it simple, if I wanted to picture the most basic pneumatic setup, what would that look like?
The absolute bare bones circuit, it's quite elegant, really. You just need 3 parts: a supply of compressed air, some kind of control valve, like a simple on-off switch for the air, and a single-acting cylinder.
Lactate.
Yeah, meaning air pushes the piston rod out, and then when you turn the air off, a spring inside, or maybe just the weight of the load it moved, pushes it back. Extend with air, retract with spring or gravity. Simple.
Okay, got it. And the heart of that is the compressed air supply. Where does that come from? What's the unsung hero here?
That'd be the air compressor. That's the machine doing the work, converting electrical power, usually, into the potential energy stored in that pressurized air.
What kind are we usually talking about for this sort of instrument air?
Mostly positive displacement types, like reciprocating piston compressors or maybe rotary screw types. They can be single stage for lower pressures or multi-stage if you need really high pressure.
And you mentioned clean air being vital. Does the compressor itself affect that? Like oil?
Hugely important. Standard compressors use oil for lubrication, and some of that can get into the air for food processing, electronics, medical uses. That's a definite no-no. So you use special oil-free compressors in those cases.
So compressing is step one, but then you've got to clean and dry it, right? It's a whole system.
Exactly. You need a proper instrument air system. After the compressor, the air is hot, so you have an aftercooler. That cools it down and condenses out like 80% of the water vapor.
Wow, that much.
Yeah, hot air holds more moisture. Then a separator spins out that liquid water and any solid bits. Then air receivers, big tanks, basically. They store the air, smooth out pressure pulses from the compressor, and let more water condense out.
And finally, drying.
Right, drying systems. Often using special materials called desiccants that absorb the last bits of moisture. If we connect this to the bigger picture, all this cleaning and drying is vital. It stops rust, protects delicate valves and actuators, and just keeps the whole system running reliably.
Makes sense. And once it's all clean and dry, how do you get it around the factory, the piping?
That's the air distribution system. You've got a few ways to lay out the pipes. The simplest is a grid or dead-end system. Cheap, but the pressure can drop a lot at the far end.
Like a long garden hose?
Kind of, yeah. Then you could have a decentralized setup with smaller compressors located closer to where the air is needed. Reduces pressure drop. But often the preferred way for larger places is a loop system. You feed the compressed air into a ring pipe that goes around the facility. Air can flow either way to the point of use, so it balances the pressure much better. You often put extra receiver tanks on the loop too to handle sudden high demands.
Like a ring road for air. Okay, now, my personal aha moment in pneumatics was learning about the FRL unit, filter regulator lubricator, and that the order you install them in is absolutely critical.
Oh, absolutely crucial. It's like the local conditioning center right before the air gets used. And yes, the order is non-negotiable if you want things to work properly.
So walk us through the correct order. FRL.
Exactly. First, F for filter. That takes out the last bits of dirt, pipe scale, maybe some oil aerosols. You can even get superfine coalescing filters. It protects everything downstream.
Okay, filter first. Lock.
Then R for regulator. This device takes the mainline pressure, which might fluctuate, and knocks it down to the steady, correct pressure the tool or actuator needs.
Got it. Filter, regulator, and last.
Last is L for lubricator. And this is important. You only use this if the specific component needs oil added to the airstream, like some older air motors or tools. It adds a fine oil mist. And critically, it goes last, right before the point of use.
Why is that order so vital? What happens if you mix them up?
Oh, it causes real problems.
Right.
Put the lubricator before the filter. The filter just strips out all the oil you added.
Right, defeats the purpose.
Put the lubricator before the regulator. That oil mist can gum up the regulator's sensitive parts and make it unreliable. It's a classic mistake that leads to failures.
Good to know. And you also mentioned water traps.
Yeah, simple but essential. Just little drains installed at low points in the piping to let any collected water out manually or automatically. Stops slugs of water from damaging components.
Okay, we've definitely got a handle on air power now. Let's switch gears to its More powerful sibling. Hydraulics. Using liquid. What's the big deal with liquid?
The big deal is that near incompressibility we talked about. This is where Pascal's law really shines. Because the liquid won't compress, you can transmit force very efficiently, even over long distances or into awkward spots, and you can generate massive forces with relatively small components.
Right, Pascal, that 17th century guy. Can you break down his discovery for us? Here's where it gets really interesting, I think.
It really is. Pascal figured out that if you apply pressure to a liquid that's confined, like sealed in a container, that pressure gets transmitted instantly, equally, and undiminished in all directions throughout that liquid.
Equally in all directions.
Exactly. Doesn't matter the shape of the container. Push on a small area, and that same pressure appears everywhere, pushing outwards on all surfaces. So if you apply that pressure to a larger surface area, like a bigger piston,
You get a bigger force.
precisely. A small input force on a small piston creates a certain pressure. That same pressure, acting on a larger piston, generates a much larger output force. It's force multiplication. That's how a tiny hydraulic jack lifts a car.
That's the magic right there. So how does that relate to pressure, area, and force in equation?
It gives us that fundamental relationship. Pressure P equals force F divided by area A, or force equals pressure times area. If you know the pressure in the system and the area of the piston you're pushing on, you know the force it can generate.
And that force does work.
Right. Work is just force applied over a distance. So the hydraulic system generates force to lift something, push something, rotate an excavator. That's useful work. And hydraulics allows for incredibly precise control and positioning, even while handling these huge forces.
What kind of liquids are we talking about? Just oil?
Usually specially formulated hydraulic fluids, often based on mineral oil or sometimes synthetic hydrocarbons. They're engineered for much more than just transmitting pressure. They need to lubricate moving parts, resist oxidation and rust, resist foaming, and crucially, maintain a stable viscosity, their thickness, over a huge temperature range. Maybe negative 50 C all the way up to 135 C.
Wow, that's a serious operating range. Okay, so basic pneumatic circuit was air supply, valve, cylinder. What's the fundamental hydraulic equivalent, and how does it handle those much higher pressures you mentioned?
A typical basic hydraulic setup involves a hydraulic power unit, that's the pump, usually driven by an electric motor, and the fluid reservoir or tank. Then you have a directional control valve and often a double-acting cylinder, meaning fluid pressure moves it both ways.
And the pressures.
Yeah, they are significantly higher than pneumatics. It's not uncommon to see systems running at, 40 megapascals, even higher sometimes. That's up around 6,000 psi, pounds per square inch. Way beyond typical air pressure.
Whoa. Okay, so the components must be seriously robust to handle 6,000 psi. What are the key players?
Absolutely heavy-duty stuff. The pumps themselves, driven by motors, are precision machines, often gear pumps, vane pumps, or piston pumps designed to generate that high-pressure flow.
And the pipes. Can't just use regular pipes, surely.
No way. You use high-pressure steel piping, tubing, and very importantly, flexible hoses. These hoses aren't like garden hoses. They're reinforced with multiple layers of braided steel wire inside the rubber casing to contain that immense pressure.
Makes sense. How do you control where the fluid goes?
With directional control valves. These usually have internal spools or poppets that shift position to open and close different pathways, directing the high-pressure fluid to one side of the cylinder to extend it or the other side to retract it.
And you mentioned pilot valves earlier.
Yes, pilot-operated control valves are common in hydraulics. A small amount of low-pressure fluid, the pilot signal, is used to shift the main spool that controls the high-pressure, high-volume flow. It allows for smoother control of very large flows.
What about safety? With that much pressure?
Critical. Every system has pressure relief valves. If the pressure starts to exceed the safe maximum, this valve opens and diverts the excess pump flow back to the reservoir, the tank. This prevents catastrophic failure, and it bears repeating. Adjusting these relief valves is only for trained personnel. It's a serious safety issue.
Understood. Any other key bits?
Yeah, accumulators. These are vessels, often with a gas-filled bladder inside, connected to the hydraulic line. They store hydraulic fluid under pressure, kind of like a capacitor stores charge in electronics. They help absorb shocks, smooth out pressure pulses, and can even provide a short burst of extra flow when needed.
Okay, power source, plumbing, control, safety. Now let's talk about the bits that actually do the moving, the actuators. What forms do they take?
Right, the actuators convert that fluid power back into useful mechanical motion. For pneumatics, we already touched on cylinders. You've got single-acting ones, spring return, or ram type.
Right, type.
Yeah, where the rod itself is basically the piston, often used for pushing, then double-acting cylinders using air pressure for both directions. Theoretically unlimited stroke, but you have to watch out for the rod buckling on really long ones.
Okay.
There are double rod cylinders where the rod extends out both ends, gives you equal force and speed either way. And for really long travel, like moving things along a track up to maybe 10 meters, you have clever rodless cylinders that use magnets or bands to couple the piston inside to a carriage outside.
Ingenious. What about rotation?
You also have rotary actuators or pneumatic motors, sometimes called air motors. They turn compressed air energy into spinning motion. They're generally compact, lightweight, easily reversible, and you can get them in a wide range of torque outputs.
Lots of options. Now, you mentioned a key difference earlier in how hydraulic and pneumatic cylinders react to load changes. Can you remind us of that?
Yes, and this is really, really important for choosing the right technology. Because hydraulic fluid is incompressible, if you stop a hydraulic cylinder mid-stroke, it stays locked there, rock solid, even if the load it's holding changes.
Locked in place.
Exactly. But with a pneumatic cylinder, because the air inside is compressible, if the load changes significantly while it's stopped, the piston could potentially move a bit as the air compresses or expands. It's not rigidly held in the same way.
That's a crucial difference for precision applications.
Absolutely. Okay, moving on to control elements. We see solenoids everywhere, little electrical coils that, when energized, pull a metal plunger, which physically shifts a valve spool. They're the bridge between the electrical control system and the fluid power system. Normally open, normally closed configurations, they're essential.
They translate electrical signals into fluid action.
You got it. Then you have the directional control valves themselves, directing the flow. And flow control valves, these let you adjust the speed of your actuator. Things like simple needle valves for fine-tuning, ball valves for quick on-off with little restriction, globe valves for throttling flow.
Deck valves.
Simple but vital. Check valves only allow fluid to flow in one direction, like a one-way street for your air or oil. Stops backflow.
Okay. Any other cool valve types?
Well, in pneumatics, quick exhaust valves are pretty neat for efficiency. You mount them right on the cylinder's exhaust port. When the cylinder retracts, instead of the air having to travel all the way back through the control valve, this provides a big local exit path. Makes the cylinder retract much faster.
Speeds things up.
Definitely. And one more for safety, especially with air hoses. Excess flow valves. These are required on larger air hoses, like over ½ inch. If the hose breaks, the sudden rush of air causes the valve to slam shut, or nearly shut, preventing the broken hose from whipping around dangerously. You install them periodically along the hose run.
Smart safety feature.
Yeah.
Okay, so we have all these components, pumps, valves, actuators. But how does the system know when to do something? What tells the solenoid to fire or the valve to shift? The brains.
Exactly. You need input elements.
Yeah.
These are the sensors and switches that detect what's happening in the real world as a part in position. Is the pressure too high? Is it time to move? And they convert that condition into a signal, usually electrical.
And many of these are the same for both air and oil systems.
A lot are, yes. Simple push buttons for manual operator input. Limit switches are very common, little mechanical switches that get physically bumped or pushed by a moving part to signal it has reached a certain position. They come with different actuators, plungers, levers, rollers, even flexible whiskers.
Physical contact switches. What about non-contact?
Right. Then you have proximity sensors, which are really cool. They detect an object without touching it. There are magnetic ones, often called reed switches, triggered by a magnet. Inductive prox sensors detect metal objects by creating an electromagnetic field and sensing disturbances. Capacitive sensors can detect almost anything metal, plastic, liquid, powder by sensing changes in electrical capacitance as the object gets near. And optical or photoelectric sensors use beams of light, an emitter, and a receiver. They can detect if the beam is broken or if light reflects off an object. Some can even detect color differences.
Wow, that's a wide range of sensing tech. Any input specific to just pneumatics or just hydraulics?
A few stand out. For pneumatics, you often find dedicated pressure sensors that screw into an airline and give an electrical signal, maybe just on-off, or an analog signal like 0–10 volts or 420 milliamps that's proportional to the air pressure.
Okay, and hydraulics?
Similar idea with pressure switches, but built much tougher to handle the high hydraulic pressures, again, providing electrical signals. And a unique hydraulic component is the flow divider valve. If you need to send equal amounts of oil to, say, Two hydraulic motors to make them run at the same speed, even if their loads are different. This valve splits the flow precisely.
Clever. So these inputs are really what enable all the automation and precise control we see.
Absolutely. They're the eyes and ears of the system, feeding information to the control logic, whether that's simple relays or a sophisticated PLC, which then tells the valves and actuators what to do. It's how complex industrial processes become possible.
What an incredible journey we've taken today, really, from just the basic idea of fluids, air compressing, liquid, not all the way through these intricate components, the pumps, the valves, the actuators, the sensors. It all comes together to make these pneumatic and hydraulic systems so incredibly powerful and precise.
It's quite something, isn't it? How those fundamental physics principles underpin so much of modern industry.
It really is. And what's fascinating here is seeing how they provide the muscle for everything from massive construction equipment to delicate robotic tasks. Hopefully you listening now feel like you have a much better handle, a shortcut even, to understanding the mechanics behind so much of the stuff that makes our world work.
Definitely worth thinking about where you see these systems in action around you.
Yeah, absolutely. So we've covered a lot of ground on how these systems work now.
Yeah, and it really makes you think. This raises an important question, maybe something to ponder. As we keep pushing automation, precision, integrating more advanced electronics, AI, better sensors, how might these already powerful fluid power systems transform even further? What new capabilities might emerge that we can only just begin to imagine right now?
Fascinating thought to end on. Thank you for joining us on this deep dive.